In this video, I'm going to be showing the different parts of FluoroMatch Visualizer. FluoroMatch Visualizer is the endpoint of FluoroMatch analysis. So after you've run the software, which is described as separate tutorials in the comment section, you will then upload your files and get these results. And then you can go through these results to annotate and confirm compounds. So now I'm going to go through each section of the visualizer platform, describing what it is and how it can be used. And then in the next video tutorial, I will go through actually annotating a data set and step by step what I would do to confirm compounds. But this is going to give you an idea of just the different aspects of PFAS non-targeted analysis that can be used to determine an unknown compound. So the first thing I would do is I would look at homologous series. Remember, and again, the comment section below shows the tutorials for homologous series as well. These are series that have different CF2 units. Now, we can look at this Kendrick mass defect plot to the left here. And again, mass defect is normalized to CF2. So CF2 is 50.0000 to infinity. And the nominal mass is also normalized to CF2. And so those should be separated by 50 Daltons if it's a PFAS subclass with CF2. So let's pull out a specific subclass. You can see the different species over here. So here's the sulfonic acids, and there's series 377. So that 377, that number, doesn't mean anything. It's just a random number that the computer assigned to that series. Okay, so here's a series, and as you can see, it does form a straight line. So this is a species with 5. You can see there's a missing point for 6 would be, and then 100 Daltons away. At 448 is there 7. So this one's 348, and this one's 448. So a difference of 2 CF2 units. And then they go by 1. So each one of these should be separated by 50. So 448 plus 50 equals 498. And as we'd expect, here's the 498 species for the C8. So this is PFOS, the most common. And then there's a C9 species, C10, C11, so on and so forth. Note that for some species, there might not be an annotation. For all of these, it seems like there are. But sometimes you may not have an annotation. The software didn't know what they are, but you can tell what they are because you know the pattern. Just another CF2 from one of the ones you've already identified. So they're all separated by 50 and have the same mass defect because the mass defect only differs in non-CF2 units. That's going to be the sulfonic acid. In this case, and that extra fluorine on the terminus of the chain is the only thing that's affecting the mass defect here. Now, as we know, the best plot to go along with the homologous series plot is the retention time versus mass to charge plot. Now, this retention time versus mass to charge plot shows a trend that should follow your chromatographic gradient. And indeed, we do see a nice trend. In this case, we don't see any outliers necessarily. But let's say we did have a dot over here or a dot down here in the corner, as we described in other tutorial videos. These would be outliers, and we could remove those. We do see in the retention time axis, the y-axis, that there are some compounds that have the same mass to charge but different retention times. These are likely to be isomers. So let's take our C8 species, which is over here, and we can shift-click to highlight multiple species. And now we're only looking at these 2 species. And this plot over here is the extracted ion chromatograms. Extracted ion chromatograms are a single mass. So you look for a single mass in this case the mass of PFAS, and how its profile looks over time. So they form this Gaussian peak through the process of diffusion as they're going through that column. And so this would be one compound, and this is probably the isomer for another compound. You can scroll over and you can see the time. So this is 3.86, and this is 3.99, indeed 3.87 and 4. So yes, there are two isomers. These are correct. And you could go through each of the isomers to determine whether or not this was an accidental mistake in the peak picking algorithm, or there actually are two different peaks. Sometimes it's nice to put a reference point. So here I put, you can see it's a different color, but another mass. So this is a different PFAS, right? CF2, 1 CF2 less. But now you can see the peaks much nicer, and it kind of extends the chromatogram. You can even see that there may have been a third peak over here if we zoom on the y-axis that was missed, so 3 isomers. Even under these peaks, sometimes they're wider, there could be multiple peaks, we just don't know, showing that there's many potential branched PFAS or other types of isomers. So, with just these 3 pieces of information, I can be confident because I got a score of A being highly confident, less than 5% false positive rate. And I can then confirm all these species, and we'll show you in that separate video tutorial how to do that. Now, the other thing that we can look at is the MSMS spectra. In this case, we have confirmed species with an A, so it's maybe not necessary to look at the MSMS, but I would never trust software right off the bat. You want to use your mass spectrometry expertise to make sure that everything makes sense. So again, let's take one of the C8 species, click on it, so one of the lower abundant ones, maybe we'll go even to the higher abundant ones. And here you can see the MSMS spectra. So this is where the fragmentation is for this species. Each of these red triangles means that this MSMS spectra is annotated, and that's an annotated fragment. So you can see various fragment annotations. I like to use this table to the right, which is the same data as over here. It's just organized in a table rather than in a plot. So here you have the most abundant, which is actually the molecular ions. That's the intact molecule that didn't break apart, C8F17SO3 with 32,000 intensity. You can also, if you scroll to the right, see the mass, 488.93, as well as the mass of all the fragments. SO3F is the dominant fragment. If we scroll over the structure, indeed it's a sulfonic acid. We would expect an SO3. And those fluorines do move around, and so it is okay to see an SO3F. They often show up in weird places. So here's our SO3F. So yes, we do have a sulfonic acid that's fluorinated. That's good evidence. We also have this C9H5F13NO2S fragment, which may or may not be very useful to us. You can see that is at mass 437. So it's this one. So I'm not exactly sure what that mass is, but it does not match the structure that we're looking for. So that's something to keep in mind, and it's highly abundant. Now, we also have some chain-related fragments, C3F7, C4F9, C6F13, and C8F17, right? And that is the entire chain if you lost the sulfonic acid. And so we have evidence that this entire chain exists. We have evidence that the sulfonic acid chain exists. And so we can be relatively confident that this is a sulfonic acid-related species. We do have some other fragments that do not make sense as far as a sulfonic acid species. Some of these larger fragments often can just be masses that were misannotated. The smaller fragments are often correct, because there's less formula that could match that mass, and so we give more emphasis on those small fragments like C3F7 and SO3F are very valuable fragments. The larger ones sometimes can be misannotated, so this could be a misannotation. Also, so this is the fragmentation plots. There is this MS1 spectra plot. It is very important to use this MS1 spectra plot to determine whether you have a pure spectrum. So if we highlight in on the precursor, you can see that there is no other peaks for this precursor. No major ones, at least. There might be some tiny ones in the noise, but nothing of similar abundance to this molecule, which means that this is a pure spectra. If you saw other peaks within plus or minus 0.5 daltons, this would be a mixed MSMS spectra, and some of those peaks that didn't make sense could come from another molecule. Still, there could be another isomer at the same time at PFOS that has nitrogens, for example. We don't know. But I would be very confident with these species, especially given that it correlates nicely in this homologous series, that it is a PFAS and did get a score of A, and I would be confident in the species. I'm just going in great detail so you can think how each fragment may or may not make sense. As you get more familiar with the software, with fragmentation, as you get familiar with mass spectrum and PFAS mass spectrum specifically, this step will become faster and faster. Often, if I'm trying to confirm a species, I'll go to the shortest chain species because there's less of a high mass, so less of a chance that you'll get incorrect fragmentation that's just too high of a mass for those fragments to be matched correctly. So here you can see it's just a bunch of SO3 and SO2 related, so sulfonic related fragments, which is great, as well as the intact molecule. So again, great evidence. Now there's one more piece of evidence when we're confirming a species. That is the isotopic pattern. So in this case, here is an isotopic pattern for C5O3SF11, which was the top ranked candidate, and no other candidates matched nicely. There's a very big difference in scores. Again, just like with the MSMS, if you're trying to confirm a member of the series in order to confirm the rest of the members of the series, because you only need one to know the rest, I often go for the lower mass ones for formula prediction because they're easier to predict and often will have more accurate predictions. In this case, the prediction C5O3SF11 matches what we got by MSMS, which is C5F11SO3H. I might have rearranged those atoms as I spoke, but it's the same atom composition. And so both the formula prediction algorithm and the MSMS algorithm and the homologous series point to this being a PFSA, specifically a C5 PFSA. So this is good. Sometimes it will not be the top ranked one as far as formula prediction. The formula prediction gets it correct 3 out of 4 times based on data we've looked at for the more abundant compounds. If they get less abundant, the formula prediction gets worse. So 1 out of 4 times it'll be incorrect. So even if it's incorrect here, but you have a lot of other evidence, especially MSMS evidence, I wouldn't worry. You can still have, but it can be useful additional evidence. One last piece of evidence for the structure is the EIC. Often you'll show blanks as well, and those blanks, if you run them, which I definitely recommend you do, is samples that were extracted, but they don't have the blood or HRLF, contaminated soil, or whatever your sample is. They're just the solvent that goes through all of your extraction processes. Ideally, also through all your fieldwork, storage, transport, etc. And so then it will look identical to your compound. That's not good. That means that it's a contamination and not a real compound. We do have blank filtering in our software built in, So most cases that should not be the case, but it's always good to check your peak shape, that you get a nice peak, that it's not just noise, and that it's above your blank signal. If we zoom in, we can see that the blank signal is extremely low, it's just noise, and our peak is extremely high, which is the NIST C target. If you do have a lot of samples, and this becomes very confusing, you can filter by the MS1 files that you want to look at their EICs. Note that it will only filter data that has MS1 spectra, and all your other plots as well. Everything is cross-referenced. One important note to make is that in this case, now we only see one dot because we clicked the dot. Wherever you click, it will filter based on what you clicked, and you have to know what you last clicked to unfilter. Then you would click again, and now everything will occur again. Also, note that we have these filters on, so you want to make sure that you don't have filters on that you're not aware of. If I'm trying to look for multiple PFAS and I only think I have one series because I have this series selected, it could be quite confusing. So that is how you would identify and confirm a single compound within a homologous series. What about discovering likely PFAS? Now there's a couple methods we can use to discover likely PFAS. So first I'm going to take off my homologous series as I mentioned, and now all of our compounds are showing. It's important to note here that not all the dots will show up. Not all your features will show up when you have too much unfiltered. The way that Power BI and the software works relatively quickly, if you have a good computer, is by not showing all the data when you have too much data unselected. So if you feel like there's dots missing here, there are. But once you filter, all of the features will show up again. Just an important note. So discovering unknowns. There's a couple ways we can discover unknowns. First is by using this flag, and in the other tutorial video I'll talk you through how to use the Excel sheet and annotate your compounds and then re-upload it into this so that you can flag compounds. But one, for example, is my flagging rubric, but you can create any kind of flags you want. It could be true, false, maybe, I don't know. You can put anything you want as a flag. It could be words, numbers, and that's your own flag for compounds. In my case, I put 1 and then a bunch of isomers of the 1 that you can still select, and 0.5 is a maybe, and 0 is no. And this is something that I haven't looked through. And so, for example, also you can have your checked. I just put 1 and 0 usually there. 1 meaning I checked that compound, 0 meaning I didn't. Again, this will only show up after you annotated your compounds, you filled in these columns in the table, and you re-upload it. So what I would do if I'm trying to look for unknown compounds is I am going to select these two, which mean everything except for those that were checked. So these are the compounds that I have not looked through yet, I have not confirmed, or confirmed that they're not PFAS. So that's one first step that you want to go through in confirming PFAS, is make sure you're not looking at the ones you already confirmed. Then I would go into this number in series. This is the first way that I would look for unknowns. So these are things that don't have a high confidence score. Here I could go through things that have 10 in their homologous series. Interestingly enough, this does seem to, must have just missed that one peak. So that was a mistake I made. So let's go for 9. Alright, sorry for that. So here's series with 5 in them. So they should have 5 peaks within the series. here's one that looks real. I can look right away at this chart and see if I see anything that forms a trend. Again, things that move like this in retention time are probably from the background because there's not a separated peak there across a large region of the chromatography. So they're either in the solvent or they're in the background. Same thing for these and these most likely. But this looks like a series. So this is series 580. So maybe I want to pull out series 580. There we go. This is why things weren't working before. I had the intensity cut off. Remember I said be very careful of filters. So this was set to 1,000 for the fragment screening, which we'll discuss soon, which meant that only things with MS were showing up. All right, now all of the peaks are showing up. None of these are annotated. They do follow a decent homologous series, specifically these three, and maybe that last one. These three could be ones that form a homologous series. You can see that their peaks are nice and that there is no blank signal. They're interesting peaks. And then the MS, it looks like we do have an SO3F on one of those species. So I can click through the different species to look at the MS to try to confirm them, just like I would before. And it looks like a lot of them have sulfonic acid related fragment, maybe SO4, but not much information. So it's pretty hard to tell whether these are PFAS or not. We can also look at the isotopic pattern, right? And again, I'm going to look for the lowest abundant one, or lowest mass. But again, this one doesn't have a good MS1 spectra. It's not very clean. So let's look at the next one. Again, pretty messy spectra. Maybe this other isomer. Finally, let's look over here. Okay, so this does look like the cleanest MS1 spectra, and it is the most abundant compound. And here we can see C12H13OF5, very low score. The darker blue is the predicted, the lighter blue is what we would guess that to be. Is the experimental. Experimental is much higher in ratio, and you can also see the mass defect is not likely to be a PFAS. It's not a negative mass defect. So probably not a PFAS, potentially PFAS, probably ignore it. But that's how we would use homologous series, is we would just go through the numbers in series, one by one. Again, I would start with the largest series because those are most likely to be PFAS. We can go through those again now that we unselected this intensity cutoff. And then look for some real series. Let's see what this one is. And it looks like we may some filter on. Interesting. So then you can go series by series and look for unknown compounds in that way. Here you can see from a very nice series. Again, I probably annotated most of the good stuff in here, so it's hard to find new unknowns. But as you were going through the series, especially if you clicked off of the ones that were annotated and looked for unknown ones, that would work very nicely. Which is not working at the moment. Seems like whoever did the flagging did it wrong. Now, One other way to look through the data, other than by looking at the number in the series, to determine unknown PFAS, is to do fragment screening. So fragment screening is we can look for a common PFAS fragment, such as C3F7, and we can even set it to be quite high, our threshold, so we only look for things that have quite an abundant C3F7 fragment. This threshold is going to depend on the instrument. And then we can see all the species that give C3F7. So there are a bunch of confirmed species, but there might also be some unknowns in here, such as this compound. And then we can click that. In this case, we can find out what its series is. Again, usually I look by series, so I'd go to 490. Some unknown, unannotated compounds. I would take out the fragment screening so we can see everything. And this does indeed look like a PFAS. And we can see, if there's any confirmed species. This is probably incorrect. It's a B. We'll talk about the scoring in a separate one. But you can see a nice trend line. It doesn't exactly have the mass defect you'd expect for some PFAS, but we look at the spectra, we can find the one that has that high spectra. Here it is. This is an amazing spectra. And we look at the MS1 again, it's clean. The MSMS spectra is extremely high, lots of PFAS-related fragments. The formula prediction does give you a highly fluorinated species. And so, to me, the spectra is definitely a PFAS species. And we have this nice trend line over here, where I would say, yes, indeed, these species are correct and are a PFAS. And then the question, of course, is, what type of PFAS are there? And that we may not know. But at least we've discovered very quickly a new PFAS series. So remember again, after you're finished with your fragment screening, always set this, not just click 0, drag this to the left. And that will make sure that it's not only including features that have MSMS data. Also make sure none of these are clicked as well. Now there's another way to do fragment screening if you want to be, for some reason my retention time now has turned negative. Do you know when you do unclick and unfilter many compounds, sometimes that will lag your computer depending on how high performance your computer. So let's say I do want something that has C3F7, but I want to be very confident that it has a carbon-40 chain. I can do an AND, and then I can click the C3F7 and C2F5, and if I wanted it to be even bigger, I could select more chains along here, and so this is a more selective process, right? You can be fairly confident, especially if they're above high signal to noise, that these are PFAS. They have 2 carbon-fluorine related chains. Very unlikely to happen by chance, unless again there's a mixed MS1 spectra. Always check for that. And then we can come up with another unknown compound, such as this 889. Again, pull out its series, look at its MSMS, try to identify it. Alright, so we did homologous series for complete unknowns, clicking certain numbers of homologous series. We did fragment screening. Now, I'll unselect these, of course, right? Always unselect the end again after fragment screening. What else do we have in our toolbox to find unknowns? Let's say we've done those 2 things, and we've identified an unknown, and we're still wanting to find more. Let's say it's a blood sample, and that's very important. We want to know everything that's in our blood, because that's what we're being exposed to. So we want to keep digging. And that's, of course, up to you and your project, how you're going to keep digging. So again, set all your filters back. This can be very confusing. If you're unsure or something's happening, you can always make sure you save when you upload your files, your Power BI, before you do anything, and also have the old file saved, and you can always open the old one without any filters set. So there's a couple things we can still do. We can filter by mass defect, normalize mass defect. So most of the PFAS, as you can kind of see these straight lines over here, these are likely PFAS. Or if I were to go into our flags or into our scores, A would be the most confident species. All right, so here's all our very confident species. They all are within this mass range. So if I wanted to find other unknowns, usually they're between, I look negative 0.05 to 0.05, although you can see that there's a few things that might fall out. So you could also do negative 0.1 to 0.1 and only show compounds within that range. Just to show that. Again, this is the normalized mass defect. So I usually go negative 0.05 to 0.05 for complete unknowns if I don't want too many compounds. And then, of course, again, we can take our filter out for A and see everything that falls within that region. And you can see quite a lot of things that look like homologous series that we could identify if we haven't yet. And here's a trend of molecules that do look like they are falling within that PFAS pattern up here. You can see the nice diagonal line along the chromatography. But I prefer, again, set your filters back when you're done. I prefer using the Kaufman because this, as you saw in the other tutorial video, and if you haven't seen the tutorial video on Kaufman analysis, you'll definitely want to focus on that tutorial video to understand these types of plots. But this is a very important plot. And this is usually put 0.95 or 0.94, and that will cut off to molecules that are likely PFAS based on their isotopic profile, their mass, and their mass defect. So it uses all aspects of accurate mass to find likely PFAS. You can see here right away how much better that filter is than the one we used previously. It's much cleaner and we can see a lot of PFAS over here. The Kaufman plot, if you scroll down, is over here. So these blue crosshairs, and again, this is described much more in detail in a separate tutorial, are EPA PFAS. Their list of PFAS, and these are theoretical values of where they lie in Kaufman space, which is the mass to charge over equivalent carbon number plot against mass defect over equivalent carbon number. Why do we plot these two? Well, one, the mass to charge is going to be much higher for a PFAS compared to a non-PFAS species if they have the same carbons. For example, PFOA, which we described in the tutorial as well, is the same structure except for it has fluorines instead of hydrogen as octanoic acid, but has nearly 3 times the mass. And so PFAS are going to have a higher mass per carbon, and we can get that carbon based on the M+1. So for PFAS, if we were to select a PFAS, the M+1 is usually let's select one over here. Quite low. So here's C4HF9. So this is an in-source fragment, and you can see the M+1 is low. Obviously, the higher masses, they get higher, but if you looked at a mass for an organic compound that didn't have fluorines for that same mass, have a much higher M+1. For that same reason we described earlier, is that the fluorines are just much heavier, so you have a much higher mass, but you still have very little carbons relative to other molecules. So let's unselect again. So that's the x-axis of the Kaufman plot, and then the y-axis is the mass defect. PFAS usually have a negative mass defect. This is not the normalized mass defect this time, it's just the normal mass defect. And so you expect them in mostly the negative region or close to zero, as you can see for many of these PFAS. And so this is the space you'd expect them in. You can see very nicely they overlay with the EPA PFAS that are defined there. If I change this number back to 0.99, showing all of the compounds, or we can put it to 1, does the same. And then we scroll down, you can see now that many of these molecules do not fall in Kaufman space. This Kaufman space, again, as you'll see in the other tutorial, is defined based on the known PFAS we have in a database. You can see they all group together, so we create a kernel density plot and then create isolines where they can fall under, and that's what we're actually changing here is these isolines. So, in summary, that's another way to identify unknown PFAS is by using the Kaufman filter to look for potential PFAS based on their isotopic profile compared to their mass and mass defect. The only other thing you could use to determine unknowns is the score, and we will go over the scores in a separate tutorial video. So with that, I'd like to thank you for watching this in-depth video on how to validate compounds using all the different plots that are available in the FluoroMatch Visualizer. My name is Jeremy Comil, CEO of Innovative Omics, research faculty at Yale University. If you have any questions, feel free to put them in the comments sections, or better yet, visit innovativeomics.com where you can download the software for free. It's open source, and you can also contact me directly there. Looking forward to hearing from you.